In the DCC lab, we use Coherent Raman Microscopy to perform myelin imaging in live animals. This video will show you what's involved in setting up your own CARS microscope for myelin imaging. Let's go in the lab with Antoine, who will show us how to set up the CARS microscope safely. A CARS microscope is a multiphoton microscope. Therefore, any scanning multiphoton microscope will do. So you'll need an objective with high numerical aperture, good transmission in the infrared, an objective with a large field of view, and non-descan detectors close to the objective. We use a video rate microscope based on a polygonal mirror scanner. As for the light source, a few options are available to you. The APE Levante or Pico Emerald, the Halifax biomedical dual output tunable laser, the refined laser Picos Duo, or the Spectrophysics Insight with a pulse stretcher. In our lab, we use a APE green Levante with a Picotrain pump. The Picotrain pump produces an output at 1064 of approximately 1 watt, and only 30 or 60 milliwatts will reach the sample. The beam is made up of 6 picosecond pulses at a repetition rate of 80 megahertz. An avalanche photodiode will not resolve the 6 picosecond pulses, but it will be sufficient to show us that the pulses are indeed coming at a repetition rate of approximately 80 megahertz. The APE Green Levante is really made up of 2 lasers. The Picotrain pump at 1064, which we use as the Stokes beam for CARS, and the OPO, from which we get the tunable output that we tune to 816.9 and use as the pump signal for the CARS imaging of myelin. Both beams are sent to the microscope independently. The OPO beam goes through its own beam path with a 1-to-1 telescope adjustable for divergence and ends at a reflective dichroic mirror that will send it to the microscope. On the other hand, the 1064 beam path has a delay line, which we will use to overlap the pulses temporarily, and also an adjustable 1-to-1 telescope to modify the divergence if needed. The goal is to recombine the 1064 and the 816 beam at the dichroic so that they are collinear when going into the microscope. A quick check shows that if they are overlapped near the dichroic and overlapped far from the dichroic, they should be almost collinear. Almost collinear. Is that sufficient? We're talking about 2 pulses that are 6 picoseconds in length, that is only a few millimeters in space, that have different wavelengths, and that must focus through a high NA objective at the same place at the same time. How can we check that to make sure that we do get a coherent anti-Stokes Raman scattering effect at the focal plane where our sample is? The beams could be parallel but not overlapped. They could be crossing at some point in space, or they could even be delayed with one pulse being behind by a few picoseconds, and therefore no nonlinear effect would take place. We need the pulses perfectly collinear. For this, we will make use of a nonlinear crystal for frequency mixing. If we focus intense picosecond or femtosecond beams into a nonlinear crystal, we will get what's called a second harmonic generation beam. In this case, the 1064 beam will generate another beam in the green, and the 816 beam will generate another beam in purple. By adjusting the orientation of the crystal, we can either double the 1064 to 532 or the 816 beam to 408 nanometers. It becomes interesting when both beams are spatially and temporally overlapped in the crystal, because in this case we will generate another color that we can use as a confirmation that both beams are perfectly collinear and temporally overlapped. We therefore adjust the relative delay of one beam as well as the divergences of both beams so that they are indeed overlapped in the crystal and generate a little bit of blue. Notice that the blue coming from some frequency is different from the purple that we get from the doubling of the 816 beam. So we can get the doubling of the 1064 into 532 when the crystal is properly aligned at the proper phase matching angle. We can also get the doubling of the 816 beam, again, when the crystal is properly aligned at the right angle. However, this sum frequency will only occur when both beams are perfectly overlapped in the crystal. This blue beam will disappear if the pulses are not temporally overlapped, as we can check by changing the delay of one of the beams. It is only when both beams are perfectly overlapped that we can send them, just like a regular multiphoton beam, into our microscope. In our case, we send it to the polygonal mirror, followed by a telescope, and then a galvo scanner for the y-axis, and into the tube lens, then the objective, and the sample. Notice the non-D-scan detectors are very close to the objective to maximize the collection efficiency. Just like any other multiphoton microscope, it is important to use very good blocking filters to avoid any leakage of the pump and Stokes beam to the detectors. Valérie will take samples to the microscope to show us images of their myelin. Just like a regular microscope, they go under the objective, which we use with a cover slip, a drop of water. We quickly find the focus, and then, for the safety of the microscope, we turn off the lights, turn on the detectors, and start imaging.